So hey there, this is Ayush and today we learn how to make the manufacturing drawing of ball screw step by step in complete GD&T. To be exact, how to make the machining drawing of ball screw. Because the ball screw is kind of a standard brought out item and we just do the machining of bearings and lock nut thread steps at the end of the ball screw as per the machine requirement. And this is our machine, ball screw based linear actuator. If you are new on this channel and interested in how to design this linear actuator, you can check out the complete playlist, link is in description. And now, before starting the drawing of any part or any assembly, we have to understand and think from three major stakeholders' perspective of any machine or product development. Number one, very obvious, the designer perspective. Like what are the important functions of the machine, how the parts are assembled in the machine, and how much tolerance, fits, GD&T controls and surface finish we need on each part to achieve the required function of the machine. And the second perspective is the manufacturing perspective, that during the machine design we have to suppose that how part to be manufactured. And most importantly, we have to understand the manufacturing process and each machining steps of that particular part. Like how the part will be located in machine's tool, like what will be the resting phase of the part. Also, we have to understand our machine shop limitation, that what are the machines we have, how much experience is our machinist. And for example, let's say we have three essential machines in our workshop: turning lathe, conventional vertical milling machine, and grinding machine, central grinding machine. Means we have to define the tolerance and GD&T controls by keeping these machines in mind. And we should not define any hard tolerance which cannot achieve by these machines, as long as the function of machine is not being compromised. And the third perspective is the inspection perspective. As a designer, we have to also think as a quality inspector. Like after manufacturing, how do we want to our part to be inspected? How the parts should be set up for the inspection, what will be the inspection sequence, and we can define all those things only with the GD&T. Also, we have to keep in mind that what are the inspection tools we have in our inspection room. We cannot define any such tolerance or control which cannot be measured, accurately. Otherwise, we will end up with no inspection or high cost inspection, and we don't want it. So let's first understand the ball screw function in this machine. And this is our ball screw based linear actuator, and ball screw is fixed with bearing units at the both ends. At the top, the ball screw is fixed with fixed support bearing unit, and then we have a coupling which connects the ball screw with the motor. And at the bottom, the ball screw is fixed in float type bearing unit. So when we power up the motor, the ball screw will start rotating and ball screw nut will travel up and down with this drilling system. So this is the overall system. Now to make the drawing of ball screw, first we have to open the ball screw in separate window. So select the ball screw and open it. And here we have two options. The first option is we can make the drawing of this screw only, and the second option is we can make the drawing of this complete set of the ball screw with the nut. And I would recommend you to make the drawing of complete set, ball screw with the nut. And the benefit of this will be we can define the GD&T relation between this nut and this screw as per given data in catalog, that we can verify that we have received okay quality of ball screw set from manufacturer as per the promise. Now to make the drawing, go to the file and go to the make drawing from assembly. And first of all, we have to bring our view into the drawing area. And now we have to resize it, rescale it. So here, go to the scale and select use custom scale. And we can try with 1:2 or we can go for 1:3. And now the complete view is going outside of the drawing area. So what we can do, we can break this. So go to the drawing and select break view. And we can break this ball screw length, something like this. And the first thing we should start with the selecting the right datum. And to select the right datum, first think as a designer. And as we can see, the ball screw is fixed with the bearings. And to understand it, let me take it to cross-section view. So as per the functional point of view, these two bearing steps should be our primary datum, but we also know the ball screw initially not comes with these bearing steps. We made these bearing steps on a standard ball screw length, and we use the turning lathe machine to make this step. And to do that, first we grip the ball screw outer surface into turning lathe chuck, and then we machine the steps, bearing steps or any other steps. So initially our primary datum should be ball screw outer surface. And now let's also see from inspection point of view. And let's say this is the inspection surface table. So how we will inspect our ball screw? So to do the inspection of ball screw, first we have to rest this ball screw on a V block, something like this. And then we will need a dial gauge. We can place this dial gauge on steps, and here we can rotate this ball screw over this V block, and we can check the steps GD&T controls with respect to this ball screw outer surface, this primary datum. But there is a problem. The ball screw length is more than a meter, and we cannot establish this ball screw on a single V block because the stability is important when we do the measurements. So what we can do, we can place one more V block, something like this, and then we can take the measurements. But in this setup, the ball screw can move axially. So we have to constrain all the degree of freedom of the part which to be inspected. So here we can add a right angle, something like this. Now our ball screw is completely constrained. So initially we can start with the ball screw itself a datum, and we can say this is the datum A and this is our datum B, this end face of the ball screw. And here don't be confused, you don't have to make any setup, you don't have to design any setup for making drawings. This is just for practical explanation. And also I want you to show you the actual mind simulation during making drawing process. For making the drawings, you just have to imagine these setups in your mind. And this is not the joke, we actually do it. So let's go back to the drawing. So let's define the datum, and this is our datum A right here, and this is our datum B. But as we give the support to this ball screw with the 2V block, so in the drawing also we can define one more datum just for indication. But here I don't want to give the datum C, it may be confusing. So what we can do, so we can name this A backtick. And now let's define the dimension. So first of all, define the ball screw diameter, which is 32 mm. And now let's start the dimensioning from this side, fixed bearing unit side. And we have this first step, and this step is just for the key cut. If you will see the design, where we just remove the ball screw outer surface to make this key. So we do not need any precise tolerance or GD&T control. So we can just define the diameter, which is 28 mm, and we can define the step length, which is 30 mm. And now we can define the key size, which is 25 mm. Also we have to define the key width, which is 15 mm, and we can give a reference from this side, and this is a size of feature, so we don't need to define the position tolerance. And now the next step is this step, and this is an undercut. And to understand this, just take a cross section here, and this is this undercut for this bearing unit, just to make sure that this bearing unit will touch this ball screw step properly. So again, we don't need any precise control over this step. So here just define the size of this undercut, and the diameter is 23 mm and width is 2 mm. And now we have our most important step, bearing step. So let's first define the diameter of this step, which is 25 mm. And as this is the bearing step, we have to define the fit. So what should be the fit? As we can see, this is the fixed bearing unit with back-to-back angular contact bearing arrangement. and then we have this nut also. So we don't need any interference fit. We can define the clearance fit. So select the dimension and here go to the fit with tolerance, and in shaft fit define G6. G6 is the clearance fit, and we have to also define the step length, and the step length is 57 mm. Now should we also define the tolerance on 57 mm? Yes, we can define it, but if we will not define any tolerance, then a general tolerance will be applicable, ISO 2768. And just for example, the 57 mm will become under this range, and the general applicable tolerance for this range is 0.3 mm. I hope you understand. And now we have to decide the GD&T control of this bearing step with respect to our main primary datum, the ball screw outer diameter, datum A. And the first GD&T controls comes in our mind is concentricity. And most of us don't know that concentricity is the most difficult GD&T control to measure. Concentricity is not what we understand in general. Concentricity is not simply control the position of one step with respect to datum step. And in this video, I don't want to go in depth of GD&T concept. We will understand all the GD&T concept in upcoming GD&T masterclass series. And as for now, I would say we cannot measure the concentricity with simple measuring instrument. Concentricity can be only measured properly on cmm. So always try to avoid the concentricity as long as possible. And instead of concentricity, use the runout or total runout control, because runout indirectly control the concentricity and circularity. So what we should define, runout or total runout? So I would say for long bearing sheet step we should define total runout, and for a small bearing step we can define only runout. But there is no such hard and fast rule. It is just like total runout will give you more precision control. So go to the geometrical tolerance and select diameter and select total runout. This is the symbol of total runout. And now how much total runout? I would say with this conventional type of turning lathe machine, we can probably achieve the 20 micron. And now we have to define the datum. And here is the thing. If we want to give the same equal weightage to these both datum A and A back knot, then we have to write these both datum in one frame, and we can write it something like this, that A dash A back dot, and click on done, and we can rearrange this. And now the next step is the threaded step, where we tighten the lock nut of this bearing unit. So let's define the size of the thread. This is our external thread of size M25 is to 1.5. This is a non-standard thread size, and we have to also define the step length, which is 18 mm. And now we have the coupling step, and here I want your closer attention. This is our primary datum, the ball screw outer surface, datum A, and this is our bearing step, which is fixed with the bearing block, and then we have this coupling step. And as we can see, we are fixing this ball screw within this bearing block. So this is our rotational axis. Means this coupling step is now directly controlled by this bearing step, not by the primary step. I hope you get my point. Means we have to define the control of our coupling step with respect to this bearing step. So we have to also define this bearing step as a datum, and to define it we can attach a datum here on this surface, or either we can define the datum attached with the dimension of this step. And we have already datum B and A, so we can define this as datum C. And here which control we should define, runout, total runout, or only position? I would say we can define only position control, because the coupling can adjust some misalignments, so we don't need any hard control. So go to the geometrical tolerance and define position tolerance, and we can define loosely position tolerance in diametrical zone, and add the datum datum C. And we can also define the fit here, the clearance fit for the coupling G6. And here we can also use some modifier to give the extra bonus tolerance. So just double click on it and we can define the maximum material condition here. Also we can apply datum shift. I know if you are a beginner you may be confused with this modifier, but we will discuss all these modifiers, advanced concept of GD&T in upcoming masterclass series. Here I don't want to go in the detail. And just for understanding, here I have defined modifier just because to save the cost of inspection. Also this will give a bonus tolerance, so it will also reduce the manufacturing cost. And if you are wondering that how we will measure this position tolerance, so let's visit the inspection setup. So here what we will do, we will place our V block below the bearing step and we will measure the variation over this coupling step. And we can verify the variation in position tolerance, because to measure this coupling step, the bearing step is our datum. And there is one more thing that we are missing, that if you will see here, this bearing is butting over this step of ball screw. And for the proper butting, we have to control the perpendicularity of this bearing step with respect to this step. So we have to define the perpendicularity with respect to this bearing seat datum. So go to the geometrical tolerance and here just select this face and bring it down, and here we just have to define the perpendicularity and it's 10 micron, which is okay, and add the datum with respect to datum C, and here we just have to align those all. And now we have to define the GD&T on this side. So first set the dimension of this ball screw length, which is 1212.5, and we can also rearrange this. And now here just first define the step diameter 25 mm and define the fits with tolerance G6. And now define the run out. So select this diameter and select run out, and for run out we can define up to 10 micron, there is no problem, and add the datum again a back dot, and we can define this step length which is 20 mm. And this is also an undercut. So for undercut just define the size. We don't need any precise tolerance or control over undercut. And then we have this circlip cut. This is the circlip, and as you can see, this ball screw step is butting with this bearing, and then we have this circlip cut. So we have to maintain this face of this circlip cut and this butting face of this ball screw accurately. And we have to consider some positive tolerance here, because if the tolerance will be in negative, means this face will be shifted under this bearing ID and we cannot assemble the circlip. I hope you get my point. So here define this circlip cut with respect to this face, which is 15 mm, and also define the bilateral tolerance here. So select the bilateral and we can go for 50 micron. And now we have to define the circlip cut size, and this cut size is 1.3 and the diameter is 23.9. But for circlip cut we have to apply the standard tolerance over this cut, and here we can see for 25 mm sub diameter the tolerance over circlip cut is minus 20 micron. So we have to define a bilateral minus tolerance 20 micron. And also we can define the perpendicularity of this bearing butting surface. So go to the geometrical tolerance and select this face, and here define the perpendicularity which is 10 micron, completely okay. Just add the datum with respect to. Now we have to define one more datum. So first define a datum, this bearing step as a datum. So select the datum feature and define this bearing step as datum D. And now here we can define this perpendicularity with datum D. And here we can also apply the GD&T control on this nut with respect to ball screw just for quality inspection. And as you can see, the permissible radial runout of the nut circumference in relation with screw shaft axis for diameter 32 and grade C7, our ball screw grade is C7, is 20 micron, and the permissible axial runout of the flange mounting surface in relation with screw shaft axis for 32 mm diameter and C7 grade, the runout is 14 micron. So let's define it. So let's first define the runout over this circumference. So select this face and here check the circular runout and set it to 20 micron with respect to datum A dash A back dot, and also we have to define the face runout. So select this face and here just define the runout of 14 micron with respect to datum, axis datum A and A back dot. Fantastic. Okay, now I feel that every dimension has been defined, and top of that we can also define the overall length of this screw, which is 1359.5. But if we will define this dimension, this will be overwritten because we have already defined all the steps dimension. So we have to make this as a reference. So select it and put it in a bracket, curly bracket, which indicates this is just for reference. I guess I'm not missing something. So we can define the surface finish. And first we should define the surface finish over the bearing steps. So what should be the surface finish of bearing steps? According to the SKF, the surface roughness of bearing sheet for diameter up to 80 mm for IT7 like H7 should be 1.6 micron, but this is a RA value. But we generally define surface roughness with RZ. So for conversion we can take this table, and for 1.6 RA we can define 6.3 RZ. I will leave this table in description, you can download it. So here choose machining required and set the roughness value 6.3, maximum roughness value Z, or we can type in RZ, it's all up to you. And here just put this over the bearing surface, but we have to rotate it. We can also make a copy of it and we can put it over this bearing step also, or we can pull this out something like this, and on the rest of the face we can go with 25 RZ. So how to define this? So to define this, what we can do is in general note, we can define the 25 RZ in open, and we can define 6.3 in a bracket. It represents the surface finish which is under bracket is applicable for the specific area where this is defined, and the surface finish which is not under bracket, which is opened, and this represent all the area where no surface finish is defined. This surface finish will be applicable. And you might be think that why I have not defined any tolerance over this ball screw length, why I leave this for the general tolerance, because there is a reason. We don't have to control this, because here we can see the ball screw one end is fixed with the floated tab bearing. So this floated tab bearing can easily adjust a large variation in ball screw overall length. I hope you get my point. And I guess I have defined every tolerance and every GD&T controls. If I am missing something, please let us know in comment. We can discuss on it. Also, you can download this drawing from video description. I will leave it there. And this is it for this video. I know this video is late as usual, but there is so many things is running in my mind related to this channel. So let's discuss the plans, and there is so many things I have to discuss with you. So in next video we will discuss all the plans related to this channel. Thank you so much for the watching.